Wait a second. Good. Perfect. So, cool. Recording. Is this working? Yep. Perfect. Okay. Finally, today, we'll come back to probability world, probabilistic world, and probability class, and also happy Thursday. Okay, so what we're gonna do today, we're gonna go talk something interesting called conditional mean. What we covered last time, we talked about joint random variables. Random variables are the way we can model the world mathematically, probabilistic way. And sometimes we have multiple random variables. If you want to study combination of them together, we use joint random variable. We start talking about just two, but we can go further. Make it vector. But they're still in a two random variables together, like x and y, or y and z, for example. We talk about sum of random variable. Sum of random variables are important. We have one example of sum of random variable we're going to finish today. And then we're going to jump to Gaussian joint, because the outcome of this week is to do estimation. You want to estimate something. It means predict something that we don't know. We want to predict something that we don't know. How? From previous information. Like maybe we know, okay, or a speed was this. And we get some measurements, and we update that belief to find the future. That's called conditional mean that we're going to talk about today, conditional mean. If you remember, I mentioned conditional probability is the best estimation. Best estimation is conditional probability. But to find the value for that one, the mean going to give you the best, answer. And when we have Gaussian, the mean and variance are everything. They give you all information that you need. Mean is the point that you are, like imagine a robot. Robot was moving with this speed, and you know that the speed was that, and you want to see what is the position of the robot, get these measurements. If you just count on measurements, that's not precise. That's not precise. We want to find something better than just measurements, because measurements are not certain. There is lots of uncertainty in measurements. So we need to update measurements. And we have some belief and measurements, combine them together as a joint Gaussian. Why is Gaussian? Because position is Gaussian, noise is Gaussian. So we want to see how we can do this prediction. That's why we are studying joint Gaussian. And conditional mean going to give us actually inference. We call it inference. Give us answer. It's not probability anymore. This is a mean of probability. So it means it's a value, it's the best value. So the conditional mean is estimation or prediction. You can call it whatever you want. We want to see how we can do this prediction. It needs some little math behind it that you probably had it in calculus. We're going to see that today. OK, so last time we talk about sum of random variables. We said sum of random variables makes a convolution. You can is kind of a sliding one PDF, as you can see, for example, PDF of x on the PDF of over the PDF of the other. We slide that together, and this integral and get integral, and its integral is actually convolution and the PDF of the sum of random variables. We proved that last time. For Gaussian, however, this part is not that related to this. But anyway, for Gaussian, we know when we add two random variables that are Gaussian, the mean is adding and the variance is adding as well, as far as x and y are independent. If x and y are independent, this is not correct. It has extra part. But if x and y are independent, we can write like that. Even doesn't need to be Gaussian. Any random variable, if we add them together, the mean and the variance is also adding as far as it's independent. If it's not independent, we have some extra here that is called covariance. We're going to see that today as well, like correlation between x and y. OK, so we explained this. We also have this picture, as you can see. This yellow and green convolve together, do convolution, and the result is this blue one. Let's do one example. Imagine we have two random variables, x and y. Both are uniform distribution, and between 0 and 1. And we want to see what is the z. Z is the sum of x and y. We want to find PDF of that. What is the PDF of z? OK, first of all, if we write these two together, f of x, y is something like that. If it's x between 0 and 1, and if y is between 0 and 1, in this case, the result is 1 because it's uniform. So it's uniform. And if otherwise, it's 0. Any question about that part? How I wrote from this, that. You can guess this is uniform. Yeah, uniform is just a line. And between 0 and 1 is like a box. Between 0 and 1, when you multiply them together, it needs to be 1. So it means that probability needs to be 1. When it's between 0 and 1 is 1. And in both cases, become 1. So we're going to get this. OK, but what we want to find this. We want to find this z, that is a convolution. Convolution of f of x over f of y when we transfer y to z minus x. Because if z is x plus y, y is z minus x. OK, so we got this from here. OK, so what we need to do? What is the process that we need to do? We need to find this integral. But this integral is from minus infinity to infinity. But we need to see how x changing, because we have d of x. We need to find actually interval of x. What is x interval? We know that x is between 0 and 1. And also, we know that z minus x is also between 0 and 1. We have these two information from where? From here. OK, we have this. If we play a little bit with this, so we can write x is, because 1 is less, z minus x is less than 1. So x is less than z minus 1. And from this part of that, and from this part of that, you also can get z minus x less than 1. So x is less than z minus 1. Am I right? No. I think I messed up. Oh, this is x minus 1. So x is, how I wrote that? Okay, so I think this is 0. This is not. Oh, that's the problem. I always make these problems here. OK, so this is 0. So it means x is less. This is equal to. This is equal to. All right, I didn't put equal here, but doesn't matter. X is less than z. And here, x minus z less than 1. That's correct. So x is less than z minus 1. So in overall, from these two, you can get, I'm going to write it here. Z is between, I put equal to z minus 1 and z. From this and this. So you can get that. So, OK, so you have this blue one. Wow, that's x. Why I make that much mistake? OK, that's x. X is between that. And also, x is between 0 and 1. From this and that, we want to see how x changing from this and that. So we're going to get one result. And the result is x is between smaller than max of, so mean of 1 and z, and max of 0 and z minus 1. Because we AND them together, this and this AND. Find x, OK? From these two, we get this. So we know x. How is x changing? Yes? Sorry, what? What? Why this? Oh, this one? Oh, maybe I made a mistake. Oh, z minus 1 less than 1. So we take x that side. Oh, OK, it's bigger. You're right. You're right, it's bigger. I made a mistake. But the rest is OK. From these two, so yeah, right now it's yes. It's good? OK, perfect. So that's good. So this is the main thing that we want to find. It means we're going to get integral instead of minus infinity to infinity, this. OK, I'm going to clean this up to write that nicer here. So this mean and max coming from that calculation that I did. And the integral of that, because f of x and f of y are in the two cases are 1, that's already 1. OK, so this is 1. We just need to find these actually values for this interval to find it. If you compute this integral, the integral, because it's just 1, is going to be mean of this minus max of this. We just need to find mean of this and max of that. OK, what else we can talk? When we are adding these two, if x is less than 1 and y is less than 1, z is between 2 and 0, because we are adding them, right? So we consider z in two situations. Z is between 0 and 1, and z is between 1 and 2. In these two cases, we find this mean and max. If z is between 0 and 1, the mean of 1 and x is what? OK, if z is between 0 and 1, so it means bigger than 0, OK, the mean of that, and less that's 1. So this mean going to be z. And max of 0 and this, because it's bigger than that, is going to be negative, so this is going to be 0. So the integral going to be between 0 and z. And if z is between, oh, sorry. Yeah, OK. If z is between 0 and 1, this is going to be 0 and z. And the others, if it's between 1 and 2, is going to be 1 and z minus 1. OK, so you just need to consider that to see if it's get negative. For example, the max of anything with negative, 0 with any negative, going to be 0. So this is simple parts. You're just going to consider these two and put them there and add them together. You're going to get this result. You can work on that at home to see. That's the PDF of z. That's what we wanted. But as you can see, we have two parts, because z is between 0 and 2 in this case. We are adding them together. Any question? That's simple. You just need to go do this kind of, I don't know, it's calculus or math, whatever. Perfect. So we are done with the add of random. It still is related, but let's go to Gaussian now. Because finally, we want to work with Gaussian. In our life, most of random variables that we are encounter are Gaussian. So it's good to know how these Gaussian variables works and what characteristic they have. But the good point about Gaussian random variables that most of the time you can get closed form solution. This closed form solution is amazing that in other distribution you cannot get that closed form. The closed form solution coming from characteristic of exponential. Like integral of exponential is easy. Differentiation of exponential is easy. Anytime you want to do, for example, maximization or minimization, in exponential, everything is in exponent part. You can remove everything out. Because exponent is very important part. Why in maximization, for example, you can get logarithm function, log function. And log is not changing the trend of the function. So you can get, if you want to maximize it, you can just get log, and nothing going to change. You get log and exponential function, they're going to cancel out each other. And what's going to stay out? Just exponents. So exponent is the only thing that is important. And it's going to lead us to the closed form solution. That's why Gaussians are very important and makes life easier. Makes life so easier. So what I'm going to talk here is about linear transformation. If you remember, we said in Gaussian, if we do linear transformation, like x is Gaussian, or normal for mu and sigma square, x plus b is also a normal distribution with a mu and a square sigma 2. We had that before. This was for one random variable. We proved that, remember? So what this means, it means if we are transfer x linearly, when we transfer x linearly, is like a vector. We just transfer x to y like a linearly with this function, a and b. So what's going to change? Mean going to change, and variance going to change too. But they're going to change based on a, not b. OK, that's the important part. But this is s squared. Same idea happening when you have two-dimensional, when you have x and y, for example. But in that case, instead of multiplication, you have dot product. So everything becomes a matrix form. So if we write the matrix form, imagine A is A1 and A2, and Z, but it's transpose of that. So it means like that, A1, A2, and Z is X and Y. So this is transformation. So what this means, X A1 plus Y A2, OK? This is A2. This is dot product. So multiplication becomes a dot product in matrix form. Also, as you can see, so same way as before, we can also prove this. What about this one? In the one variable, we had a square, sigma square. So sigma square in joint Gaussian become capital sigma. That is, capital sigma is defined like that. So that's a definition of joint Gaussian random variable. If you have joint Gaussian random variable, mean is mean of x and y, and sigma, or here we call it covariance. This is not variance anymore. Variance is when we have just one variable. But when we have multiple variables, we have covariance, because we have off diagonal here. So this off diagonal is appear here, that's showing relationship between x and y. These two are still variance. This is variance. This is also variance. Sometimes we write that sigma xx, sigma yy. It means how y corresponding to y changing, OK, regarding each other. But these two is off diagonal. And this is called covariance. That's showing correlation. Correlation between x and y, or y and x, and that's equal. They are equal. It's transpose of each other. So these two are z yx is equal to transpose of that. So sorry, not inverse transpose. Transpose of that is sigma xy. So that's interesting. So the off diagonal most of the time is something constant or something similar, or 0. If it's 0, it means there is no dependency between x and y. So this is showing dependency between x and y. Let's make it in a, let's visualize it. Imagine you have x and y. This is x and y. And this is PDF. You have a 3D. in this case, one point here in x and y, in that plane, this is in a plane, this PDF is coming out of the plane, okay? And how we can see that, so this, how x and y changing regarding together, if sometimes this is just a circle, like a bell shape that coming out of the plane, but equally distributed. So in that case is actually circle shape. If x and y are not actually related to each. But if there is a correlation between x and y, it become ellipse shape. So let's show that one. In this case, it's going to be like that. But in 3D shape. It's in 3D shape. It's coming out of the plane, you know. This ellipse shape showing how x and y correlate. There is correlation between x and y. If there is no correlation, it becomes circle. Maybe in your other class, you learn about whitening. Have you heard about whitening in your signal processing? Have you had a course like that? Yeah, something like that. In whitening, you are making this ellipse shape a circle. You're removing correlation. Yeah. Well, we can see that later. Okay, so I'm just going to make you ready for this joint Gaussian random vector and go to conditional random variables. Okay, let I clean this up. Any question about this stuff that I mentioned? Like this shape, and it's like one-dimensional. In one-dimensional, we had one x and one PDF. In two-dimensional, we have x and y. Again, we have PDF. But PDF is like make it 3D. So intensities here, they have different intensities, and intensities are around the mean. This is the mean. We are around the mean. When we are the mean, it has a highest PDF. It has a highest field. That's why it's a Gaussian shape. It's like a bell shape, but a 3D shape of bell. But this shape is not symmetric. It's like an ellipsoid in 3D, an ellipse in a 2D. And this angle, how much is like a long? It depends how much x and y are depend on each other. Perfect. So let's clean this up. Let's have some explanation. The stuff that I already talked about, I also talked about, wrote them here. This block Z, we also call this block covariance, because each of these can be a one block. You know, in matrix, we have so many ways to can make our life simpler. One of the way is just make it a blocks. All of the matrix can be one block, but this sigma x also can be one block if you have more than one dimension for x. In here, we just have one dimension, but that sigma is variance, is one number. But imagine x is also two-dimensional or three-dimensional. In that case, that's a block, the matrix block. Anyway, the block sigma captures both internal variance and cross relationship. This cross relationship called covariance, that's showing correlation between these two. And the joint Gaussianity ensure that any subset and any linear combination remain Gaussian. This is good part about Gaussian. It makes a closed form. We're going to see that we can play with that, and we do transform. This is transformation. Did you get that? When we multiply by a vector like A, we are transferring x here as z, sorry, transferring z to another space, to another point. And this is transformation. This transformation stay Gaussian. Why? Because that's Gaussian shape. As you can see, the mean changing to this mean, and the variance changing to that variance. Okay, let's go for joint PDF. What about if you want to write joint PDF? Actually, I had this for many dimensions before. I changed that to 2 dimensions. If you printed the previous version of that, it should be more complex than this. But this formula is just for 2 dimensions. It means dimension of x is 1 and dimension of y is also 1. But in reality, x can be m and y can be n, for example. But don't worry about that part. Right now, we are just x is 1 dimension, y is 1 dimension, x and y are 2 dimensions, okay? Dimensions. This is exponential. If you remember, for one random variable, the exponential was like that. F of x, I just want to show you that this is exactly similar, but just in a matrix form or in a vector form. This was for one random variable, 1 dimension, x minus mu square to sigma 2. Okay, we already explained that blue one. That's for one random variable. So for one random variable, a Gaussian PDF is like that, showing that that bell shape. And sigma is a variance. Sigma square is a variance. And mu is a mean. This is for 1. If we transfer this to 2, what we're going to happen, we need to make this part a square. So that's why here we just have 2p. If we have m and n, we need to have m plus n as a power. But we can see that in a vector for, oh, what I did. Anyway, this is exactly that. But instead of sigma square, we have sigma. And you remember, sigma square was down, so we have sigma square, a capital sigma inverse that's coming up. So this form is called quadratic form. Okay, why I'm explaining this too much? The reason is we're going to remove all the parts of exponential, all of those constants out. We don't need them. The only part is important for us, this quadratic form, that is actually very well formed, very good form, that we can simplify that and take out whatever we want from this. And as we explained before, this sigma z is like a block form. We have z of x, z of y, and sigma y x and xy that are transpose of each other. So we already explained that. OK, so let's see what we can take out from this. First of all, this density completely explains everything about these 2 random variables. Just this formula explains everything. The only variables that we need, the only unknown that we have here are mu and sigma. The sigma is that, and mu is the mean. What is mean? Mu x and mu y. Okay? And the exponent part is an important part. And this exponent part actually, is it the formula for ellipse, isn't it? Or ellipsoid shape in a 3D ellipsoidal shape. That's the formula for ellipsoid. So this is the quadratic form that we're going to see how we can play with that. OK, so that was the general information about multiple Gaussian random variable. OK, put that away. Let's go to conditional now. Any question about that? It's nothing new. It's just Gaussian. We just make a dimension 2. When we make dimension 2, instead of having a square, we have quadratic form. And instead of having, for example, a square root of 2p, because it's 2, we make a square of that, and the square root is going to get disappear. OK, so let's go for another part that is conditional probability. For conditional probability, we know that probability of x given y is probability of x and y over probability of y. You remember that? That's a conditional probability. OK? But P of y is not important for us. Why? Why we are not interested to y? Because x is something that we want to optimize. X is our variable. X is our state. Y is, for example, just measurement. Sorry. Measurement. I don't know why it's not typing. Anyway. Measurements. So y is measurements. Like example, y can be something. It's not something that we wanted. X is something that we want. X is something that we want to estimate. And in this case, if we just want to estimate x, if you want to just maximize probability to find x, y is not important for us. Y is like a constant. That's why we have a proportion here. This showing proportion. This proportion showing when you do maximization or minimization, just that part is important for us. OK, so this means, OK, we remove that part. That's good. This is one of the things that we always need. And what about this? This is joint Gaussian. This is joint Gaussian. And right now, we already explained joint Gaussian. And we can use whatever we know about it. So what we know about it, if probability of x and y are Gaussian, probability of x given y is also Gaussian. In this case, proportion of this coming from this x, the rest of the constant values, we put them out because it's just proportion. And this proportion is like that. Instead of mu, we put mu, instead of mu xy, we put mu x given y. Instead of z xy, we put z x given y. When x and y are Gaussian, x given y is Gaussian too. Look at that. They are a proportion of each other. That's why we can write it like that. So this is the one important part that we can get. From this, we can see that, OK, x given y is also Gaussian. And when it's Gaussian, following Gaussian formula. And this is Gaussian formula. This is a very important part because, as you can see, we need to find these three parts. This is our estimation. We want to see how we can find this, mu x given y. But we have some information here. The information, I'm going to write that with another color to emphasize this paragraph. We know that some mathematical actually trick that we can use for quadratic forms. Those mathematical coming from two trick, that is one called block. Actually, it's just one, not two. Block representation, that is the formula for sigma. This completing the square is the trick. What about we just make this as a block way matrix and multiply them all together and make a complete square and find the new mu based on those values? This is how we can find the actually a closed form solution out of the Gaussian conditional probability. As far as is Gaussian, we can do all of these cases. Why? Because the Gaussian makes this beautiful quadratic form. And quadratic form, with some tricks, can change to a complete square. When it gets to complete a square, you're just going to remove this part away and just have this out. So we can find that. OK, this is how we can do that. I'm just going to explain this part a little faster because this is something that you had in calculus. I'm not going to ask you in exam this test. The last formula is important to know. So we can consider this inverse math because computing inverse is very hard in computer. Even if we want to consider complexity, complexity is O of n3. It's very complex. Computing inverse is a hard part for hardest part, I can say hardest part in computer. Because it has lots of operation to do. It has like 3 loops to do inside each other. That's why complexity is order 3. But this gonna help us to make it easier. So imagine we know this inverse. So we just consider it A, B, C. And as you know, B and B transpose are transpose of each other. B is equal because sigma xy is equal to sigma yx. So it means the transpose of zyx. So that's why these two are related to each other. So we don't need to have 4 values. We just need 3. OK, so that's important. And the rest is coming from, so first thing that we need to do is just that. The rest is all extra. Don't need that. The other things that you need to know is a completing a square trick. Completing a square showing how a formula like that can be written as a complete square. Complete square is this. So this is equal to, we can take A out, x here is square, something with x, and another value here. This is the complete square that's going to help us to find mu out. OK, so based on these 2 things that we already explained, the block representation and completing the square, let's do the math here. So this is all I explained this. We don't need this. This is just extra. Yeah, the math is here. We have that. We just need to do substitution. Instead of this, we put this block representation. We multiply them together. And then we do some calculus or linear algebra. And so as you can see, we have one here that is the form of quadratic form. We have another one here, quadratic form. And so these two are going to help us. And using completing the square, we can make this. That's the last formula. You need to just work with that a little bit, and you're going to take that out. And that's everything that we need. This is the complete form. We made a new square. We made a new square. So this part, as you can see, we have mu x here. We have another mu x here. And what about this? And this part, so this part is actually mu x given y. As you can see, this is equal. Oh, sorry. This part. Yeah. So this is mu xy. So these two tricks help us to find the exponent. Exponent is the part that we are interested in. And we write exponent like this. And when we write like that, we can take this out, this part out. So this part is mu xy. And still we have one a that we don't know. We just need to compute a. How we compute a, that's also easy. How? We know this multiplication is like that. And as far as there is no correlation between y and x, so we can find this as well. If we put that, this is the last formula. I'm not going to ask you how to compute this, but you need to know how we use this calculus and linear algebra to get this. This is the main thing that we need to know. And what it shows that mu xy is mu x plus something new. This something new has two parts. One is this part. One is this part. OK? Let's explain this in a way that you understand it with robotic view. OK? So this is like we are estimating position of the robot. X is the position of the robot. And y is measurements. So y is measurements, and x is the position of the robot. So we want to say the next position of the robot, x given these measurements, is previous position. This is previous position. Or I can say belief, sorry, belief. About the position, believe about the position, plus some extra information. This extra information is related to y and mu y, and some variance between these two. But this is always positive. So this is always positive. It's showing that we are getting close to reality. So we are improving our belief in this case. I will explain this much more later. I just want to give you idea. I'm going to go to the example, and we're going to talk about that more next class as well. So let us just talk about this interpretation that I explained. mu x is a baseline, is also called a prior information. As I explained it, mu x is like or belief. We believe the target going to be here. We believe the robot going to be here. This is the mu x. Baseline or prior mean. This part, this is how much x is linearly related to x. This is how much x is related to y. And this part is deviation of the observed y from the mean. Deviation from the mean. And this is together act as a correction part. We are kind of correcting our belief. This is the correction part. This is our belief. We are correcting our belief. This is actually the structure of Kalman filter that we're going to see that soon, next week. Because in Kalman filter, exactly we are doing that. We are estimating the position of something based on new measurements. We have some belief. We are guessing, oh, maybe he's here. How we update it? We read measurements. So that's how actually estimation works. Let's do one example to understand what's going on. So we have, for example, a radar that try to track like airplane, for example. So let's see which color is which. You can see here, prior. OK. So this blue is prior mean. So it means or belief, or is actually a prediction. We also call it, we predict it, and then we update it. So this is our belief, and this is the measurements. But we just have these two, but we want to find the best estimate based on this belief and these measurements. That's called estimation. That's called prediction. That's something that I want you guys understand. It's something that you need to get out from this class is this. You have two values. You have some belief. You have some measurements. You want to see what is the best mean. And this mean is a conditional mean. You need to find conditional mean. You need to find mu of this belief is x. This measurements is z. Oh, sorry, y. This is not x, it's y. This is z, and this is mu of y given z. You want to find that. But how we can find that? We already have the formula now. We already have formula. So this formula showing the new update, the update is coming from our prediction plus our correction. We are correcting that. OK? So first, I need to explain a little bit this part, explain a little bit the question. So we have y. Y is our prior random vector. I call it here vector, but you can imagine just one value. It doesn't matter. And z is the measurements. Measurements is y plus some noise. And this noise is a white noise. Zero mean is a white noise. And zero mean noise. And then the new random variable that has this y and z, because we have two random variables in this case. One random variable is the measurements. One random variable is our belief. We have two random variables. So these two random variables make a Gaussian joint random variables with mu like that and sigma like this. Why this sigma is like that? Because of this. When z is y plus omega, sigma y is sigma y, sigma z is sigma y plus sigma w. This is coming from that. And sigma y z is also equal to, because this z plus y is equal to sigma y plus sigma w. Oh, let I write this nicer. We have a little time for that. Okay. Okay, so sigma yz is equal to let's see how, oh, here, sorry. Sigma yz. This sigma yz is a covariance. Is sigma, I can write it in a covariance way. So covariance y and y plus w is equal to covariance y and y. Oh, we already wrote that. Oh, y and y, and covariance of y and w. Y and w covariance is 0, so this is equal to covariance of y. Because y is always, this, we consider noise is independent than w. That's why this is always 0. So this is, that's why this, I just wanted to explain how this sigma y coming from. We don't need that, but later we can see that more. We're going to get used to something like that. I just wanted to show why covariance of y plus sigma is covariance of y. The formula coming from that calculation, but we can talk about that later as well. Anyway, the rest is just a substitution of these values. We have this belief. We have this sigma y. We have sigma w, and we have z. And if we put that in a formula, we're going to get this. And we believe this is better than previous belief. This is better than previous belief. We can prove that next class. How we can prove that? As far as the covariance let smaller, or as you can see here in this picture, you can see the covariance. This is the covariance for the first one. This is the covariance for the after. We didn't calculate it. We didn't calculate covariance. Next class, we're going to compute that as well. OK, that part was a little tricky, but we're going to play with that a lot. Don't worry if you didn't get all the points. We're going to play that a lot, and you're going to have lots of examples. OK, have a great day, rest of the day, and holiday. I mean, weekend. You have class tomorrow, of course. Let's stop this.